Hello everyone, welcome back. In this video, we will be talking about the maximum and minimum values. And here in this section, we are going to be covering only the analytical aspect of how to find the maximum and how to find the minimum, whether it be absolute maximum or absolute minimum or local maximum or local minimum. So we also, in this chapter, we are going to be seeing a lot more about the graphs of a function in general, how to do a comprehensive graph of a function. And also we are going to see how maximum and minimum, the concept is important in real world application problems, such as optimization problems. So it's such a beautiful and interesting chapter. So let's first see how to find the maximum and minimum values from the graph and how we define them. Let's see be a number in the domain D of a function f. Then f of c is the absolute maximum value of f if the value at c is more than or equal to value of f of x for any x in the domain D. So that should be the highest point. So if you notice in this graph, this is the highest point. This problem, in this graph, it occurs at 3f of 3, which is 3, comma, in this case, it looks like 5. Right? So 3f of 3 is the absolute maximum point. The absolute maximum value is the y-coordinate of the absolute maximum point, which is 5 here. So f of 3 equal to 5 is the absolute maximum value in this case. Same way, the value absolute minimum value of f in D on D, if f of c is smaller than or equal to f of x. The y value at c is smaller than or equal to any other y value in the graph for all x in the domain D. That is important. So in this case, you notice at this point, 6, f of 6, which is actually 6, comma 2, is the absolute minimum point. The y-coordinate, f of 6 equal to 2, is the absolute minimum value. So if we write that, so f of 6 equal to 2 is the absolute minimum value. So anytime the question asks about the value, you have to focus your attention on the y-coordinate. You can call the pair as the absolute maximum point and absolute minimum point, the ordered pair. Same way, we will define the local maximum and local minimum. The idea is same, but in the neighborhood of a point. So if the maximum occurs in the neighborhood of a point, then that maximum is called local maximum. If it occurs and the minimum point occurs in the neighborhood of a point, then it is said to be local minimum. So it is local maximum value of f if f of c is more than or equal to f of x near c, so in the neighborhood of c. Same way, you will have local minimum of f if f of c smaller than or equal to f of x. F of c is smaller than or equal to any other y when x is near c, in the neighborhood of c. So you see in this graph some peaks, some valleys. So if you look at the peaks, there is a peak here, there is a peak here. So those are called local maximums. So some of them could be absolute maximum. Let's go one by one now. So if you notice here, B, f of B, okay, and D, f of D. So you see two peaks. They are local maximum points. And you can say f at B and F at D are local maximum values. And do you see valleys? Yes, we see a valley here. There is a valley here. So there are two local minimums. So F at C, so you can say C, F of C, and E, F of E are local minimum points. So F at C and F at E are local minimum values, the y coordinates. Is there an absolute maximum in the graph? Is that the highest point in the entire graph? That is going to be this point. That is going to be the absolute maximum. What is the smallest? The smallest here is this one here. That is going to be the absolute minimum. You can say F at D is the absolute maximum value, and F at A is absolute minimum value. So F of A cannot be the local minimum because there is no part of the graph on the left side of F of A, and it occurs at an endpoint of the interval. So local max, absolute maximum and absolute minimum can occur at the endpoints of the interval, but local maximum or local minimum cannot occur at the endpoints of the interval. Okay, so make a note. So local max and local min cannot occur at the endpoints of the interval. The endpoints of the interval where the graph is defined. Absolute max or absolute min can occur both at the endpoints and also locally within the interval. Right? So here we notice that F of the absolute maximum is occurring inside of the interval. The absolute minimum is occurring at the end point of the interval. Okay. All right. Let's take an example. The graph of the function f of x equal to 3x to the power 4 minus 16x cube plus 18x square, where x lies between -1 to 4, is shown in this graph. What are the local max, absolute max, local min, and absolute min? So let's take each one of these points here and we'll analyze. What about f of -1, which is equal to 37? I'm focusing on this point. So what do you see there? It seems to be the highest point in the entire graph. So that is going to be the absolute maximum. Because it is the y coordinate, so it's absolute maximum value. Right? Then what is happening at 3, -27, this point, 3, -27. So -27 seems to be the lowest among the y values. It's in the entire graph. So we can write f of 3, which is equal to -27 as the absolute minimum value. Note here, absolute minimum is occurring inside of the interval. Absolute maximum is occurring at the end of the interval. So absolute minimum or maximum can occur at the endpoints or locally, but local cannot occur at the endpoints of the interval. That is important. Now, where else do you see some peaks? I see a peak here. So I can say f of 1 equal to 5 is a local maximum. It's a local maximum value. Are there valleys? Yes, you see a valley here. You also see a valley here, right? There are two valleys. So f of 0 equal to 0 and f of 3 equal to negative 27 are the two local minimum values. Note here, the value f of 3 equal to negative 27 is both an absolute minimum value and also a local minimum value, right? So an absolute minimum or maximum can occur both at the endpoints of the interval and inside of the interval, but local max or local min cannot occur at the endpoints of the interval. Extreme value theorem. If f is continuous on a closed interval AB, so we know what closed interval means. Continuous means there should not be any gap. It should not be any hole or breaks in the graph. Then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d on the closed interval AB. So you're guaranteed, the function is guaranteed of a local max, an absolute maximum and an absolute minimum. Another word for absolute maximum, so let me mention that over here. Another word for absolute maximum is global maximum. So absolute maximum also means, or global maximum. Local maximum also means relative maximum. Same way, absolute minimum also means global minimum. Local minimum also means relative minimum. It's another terminology. Now, when do you say a function, a graph will definitely have an absolute maximum and an absolute minimum? When it is continuous on a closed interval. So these two are requirements. So in this first graph, you notice that it's a continuous graph. It's on a closed interval AB. So there is a peak and there is a valley, right? So there is a max and there is an absolute minimum. The next graph is also continuous on a closed interval A to B. So there is a peak here, which is absolute max. And there is an absolute minimum at this point. So there are two peaks in this graph, the absolute maximum. And there is an absolute minimum in the graph, which is this one. That is the lowest of all. Right. So for in this graph, the graph is a continuous function. There is no hole or break. And therefore, it's also defined on the closed interval AB. That's why you are able to find an absolute maximum and an absolute minimum. So if we look at the next graph, you notice in the first one, figure 8, you notice that there is a break at the point at 1. So you notice that this one has an absolute minimum. That is only absolute minimum. Is absolute minimum. But the graph does not have an absolute maximum. Why is it? Because the graph is discontinuous at 1. So in this graph, there is no absolute minimum because there is a hole at 1. So it's not, there is no absolute minimum. Same way, there is no absolute maximum because the graph goes on and on. This is because there is a discontinuity at x equal to 2. So there is a discontinuity at x equal to 2, or there is a vertical asymptote at x equal to 2. So no absolute max, no absolute min. So continuity on a closed interval is important. Both conditions are important for to have an absolute maximum and absolute minimum in the graph. What is Fermat's theorem? Fermat is a very great mathematician. This theorem is based on his name, Fermat. If f has a local maximum or minimum at the point C, and if f prime C exists, then the derivative at that point will be equal to 0. If there is a peak or a valley at a point, and if the derivative exists, then the derivative has to be equal to 0. That means there is a horizontal tangent at that point. The derivative equal to 0, that means it's a horizontal line. Okay. If you look at this, in this example, f of x equal to x cube, the derivative is 3x square. And if you notice, if you look at the derivative at the point 0, if you plug in x, the derivative at x equal to 0, it is 3 times 0 square. So you get 0. So you get the derivative equal to 0. Even though the derivative is equal to 0, at that point 0 in this graph, there is no local max or local min there. It only says that there is a horizontal tangent there. This is because what we are trying to say here is the derivative equal to 0 doesn't mean the graph has a local max or min. The converse of Fermat's theorem is not true. If f has a local max or min at C, then, and also the derivative exists, and then the derivative will be equal to 0. So converse to Fermat's theorem is not true, need not be true. So here, f prime 0 equal to 0 does not mean, does not imply f has a local max or local min at x equal to 0. So mainly we say the converse to Fermat's theorem need not necessarily be true. So in the next example, we are taking the absolute function f of x equal to absolute x. There is a corner at the point 0 we know, right here. The graph is actually continuous everywhere. The graph is continuous in the entire real line. And at this point, there is a minimum. A minimum is occurring. Even though minimum is occurring, but according to Fermat's theorem, it says that if the derivative exists, it will be equal to 0. But at the corner, f prime 0 does not even exist, does not exist. And even though f of x is continuous, absolute x is continuous on D and the entire real line, But because the derivative, and also it attains the minimum at C, and it attains the minimum at 0, but the derivative does not even exist. So in these two examples, what we are trying to say is that Fermat's theorem is only one way true. If f has a local max or min at C, and if the derivative exists as well, then the derivative will be equal to 0. Next definition is a very important definition. A critical number. Critical number of a function f is a number at C in the domain of f such that f prime C equal to 0 or f prime C does not exist. The derivative of f at C does not exist, or it is equal to 0. The derivative equal to 0. So let's combine this concept with the definition that we did in Fermat's theorem. If f has a local maximum or minimum at C, then what did we say about Fermat's theorem? And if the derivative exists, it will be equal to 0. So if the derivative exists, it will be equal to 0. Then it is possible that the derivative doesn't even exist. Okay? So what it means is that we can combine and say if f has a local maximum or minimum at C, then C has to be a critical number. So what do you mean by critical number? Either the derivative equal to 0 or the derivative does not exist. So this following method gives us the method of finding the absolute maximum and an absolute minimum. The closed interval method to find the absolute maximum and minimum values of a continuous function f on a closed interval AB. Step number 1, find the values of f at the critical numbers of f in the open interval AB. Step 2, find the values of f at the endpoints of the interval. Step 3, the largest of the values from steps 1 and 2 is the absolute maximum value. The smallest of these is the absolute minimum value. So this is known as closed interval method because in a continuous function on a closed interval is guaranteed to have an absolute maximum and an absolute minimum. That's what we saw in extreme value theorem, right? So how to find those extreme values, absolute maximum and minimum, is what this method is telling us. So find the values of the critical number, and then you find the values of f at the endpoints of the interval. Then the largest of the steps 1 and 2 is absolute maximum. The smallest is the smallest of step number 1 and 2. Find the absolute maximum and then minimum values of the function f of x equal to x cubed minus 3x squared plus 1 in the interval -1/2 to 4. First of all, is it a closed interval? Yes, it is a closed interval. What are the endpoints? Endpoints are -1/2 and 4. The question is to find absolute maximum and absolute minimum. So step number 1, find the critical points. What are the critical points? The critical points are points where the derivative equal to 0 or does not exist. So f of x being a polynomial, the derivative will exist at every point. It's a polynomial, right? So the derivative will exist. So what is f prime x equal to 0? Which means 3x squared minus 6x equal to 0. This implies 3x can be taken out. So x minus 2 equal to 0. So x equal to 0, x equal to 2. Before you conclude their critical points, are they lying between -1/2 and 4 in the given interval? Yes, both 0 and 2 lie between. They belong to -1/2 to 4, right? They belong to this interval. That is step 1. Then what is step 2? We have to find out the maximum of the endpoint. We have to find out the values of f at the endpoints. Find the values. In fact, we have to do the values at these points. Find the values of f at the critical points. Namely, x equal to 0 and x equal to 2. So f at 0 equal to, so substitute x equal to 0, which will be 1. F at 2, substitute 2 in the place of x. So that is 3 times 2 squared plus 1. So 8 minus 4 times 3, 12 plus 1. So which is -3. So we have f of 0 equal to 1 and f of 2 equal to -3. All right, now we have to find out the values of f at the endpoints. Find the values at the endpoints. What are the endpoints of the interval? -1/2 and 4. So we have to evaluate f of -1/2. So you plug in -1/2 into x in the original function. So it is -1/2 the whole cube minus 3 times -1/2 the whole square plus 1. So this will be -1/8 and minus 3 over 4 plus 1. If we take the LCD as 8, so it will be -1 minus 6 plus 8 divided by 8. So it is 8 minus 7, that will be 1 over 8. All right. So we've got one other value at the end point. The critical points are done. What is the last endpoint that we have to check? F at the final endpoint, which will be 4, the right endpoint, which is at 4. So which will be 4 cube minus 3 times 4 square plus 1, which is 64 minus 48 plus 1. That will turn out to be 17. So we have got all the values that we want. So now the conclusion is, what is the highest? So absolute maximum value which of these values that we have evaluated is the highest? So it is definitely f of 4 equal to 7 is the highest. F of 4 equal to 17 is the absolute maximum. What is the absolute minimum? The lowest of all the values. So we have a -3, we have a 1. So the only negative number here is -3. So which is at f of 2. It's -3. So absolute minimum value is -3. Absolute maximum value is 17. That's the answer to the problem. So there are some practice questions in this exercise. Make sure to watch the video. This is done in the section video. Problem number 5 is done in the section video. And also these problems, number 53 and 65 are done in the section videos. Please watch them. Hope this video helps. Please make sure to watch the next section of this chapter video, which is section 4.2.